If I showed you this problem, how would you solve? It says there's a planet moving in a circular orbit around a star. We have the mass of both objects and the distance between their centers. We're looking for orbital speed. Pause the video and, to your neighbor, explain briefly how to solve this problem. Pull out your equation sheet and see if you can recollect the way we approach this type of a problem. Okay, we're coming back. We've taken some time to figure this out. Here is the approach we take. We start out by equating the net force on the planet with the force of gravity. This was Newton's big revelation. It says that objects in orbit are falling. They're in free fall. Gravity is the only thing they feel. Pause the video. If you didn't make it past this step, then pause now and try to answer the question, what do we plug into the left side of this equation when we solve these problems? What do we plug into the right side? Pause the video and try now. Okay, here's the answer. To the left, anytime an object moves around a circle, the net force is mv squared over r, and yes, the planet here is moving around a circle, so that equation applies. What do we plug into the right side? We apply Newton's law of universal gravitation. The force of gravity pulling the planet and causing it to turn is coming from attraction with the sun. So here is our approach. We have mass planet, massive star, or massive sun. And in all of these problems, r, in every equation, r is the center-to-center distance between the objects. Okay, what's the next step when we solve? The next step is to simplify. So pause the video and rewrite this equation, but with the simplifications that we have access to. Okay, here we go. The simplifications are cancel out one of the mass, cancel out the mass planet from both sides, cancel out one of the r's in the denominator, and that gives us this. Now, from this point, we proceed by solving. We plug in the mass of the star, we plug in r, we square root both sides, and we solve. But we're going to do something a little different. We know that whenever an object moves around a circle, there's another equation for its speed. Pause the video and see if you can figure out what equation we're going to put into place right here. Check your equation sheet and see if you can figure this out. All right, here we go. The equation that we're going to use is distance over time in one complete period, once around, the distance traveled is one circumference. Pause the video again, see if you can distribute the squaring to everything inside, and then see if you can simplify the expression by putting all of the r's on the left side and then putting everything else on the right side. So again, pause the video, simplify by combining all of the r's on the left and then putting everything else on the right side. Welcome back. Now, before we double check the algebra you just performed, let's motivate the very thing we've done. Why are we grouping the r's together? Well, here is the question that we want to ask. How does the orbital radius of the planet depend on the orbital period? And so you can imagine, for example, well, there are 8 planets in our solar system. They're all at different distances away. And so Mercury, the one that's closest, how does its close distance change the period it takes, the time it takes to go around the sun once? You know, for something really far away like Jupiter, how does its large orbital period change the time that it takes to go around once? That's the question we're asking. And so you can see from the phrasing, r is kind of like our dependent variable. It's our y-axis quantity. It's the thing that depends on some other input or some other independent variable. So we need to isolate r, or at least get the r's together on one side. Okay, now let's check your algebra. You distributed the squaring to everything in parentheses. That gave us 4 pi squared r squared over t squared. And then you moved the r to this side, which is going to make r cubed. You moved the t squared to the numerator, multiplying both sides by t squared to get rid of it, away from the r squared. And then to get rid of the 4 pi squared, you divided both sides by each of those things. When we put all this together, this is what we get. So here's my question for you now. Pause the video and try to articulate in your own words, how is r dependent upon t? Or in other words, what's the proportionality between r, the orbital radius, and t, the orbital period? Okay, welcome back. You've made an attempt. We could write the proportionality like this. R cubed is proportional to t squared. That means if you make a plot with r cubed on one axis and t squared on the other, you should get a directly proportional graph, a straight line through the origin. And now pause the video one last time. My final question for you. What does the slope of this graph equal? We've already got this equation into y equals mx plus b form. So identify from this equation, pause the video, and identify what the slope is equal to. Okay, welcome back. Here is our y quantity, here is our x-axis quantity, and all of this constant here, the coefficient to x, must therefore be the slope. The slope of this graph will be the universal gravitational constant, which we know, times the mass of the sun over 4 pi squared. And what you see, this graph you see here, you will produce in Excel. So here is our procedure. You'll go online to NASA's website. You'll find planetary data. We'll use 9 planets, in fact. We'll include Pluto in the list. And we will find for each of the 9 planets, how far is it from the sun? What's the value of r? We'll also find for each of the 9 planets, how long does it take to go around once? What's the orbital period? We'll make a plot of regular old r against regular old t. Then we'll create a plot of r cubed against t squared. You'll copy your data tables, just take screenshots, and paste screenshots of your data tables, and the 2 graphs, those will all go into your Notability file. Then you'll get the slope value from your trend line equation. You'll plug it in along with g and 4 pi squared, and you will calculate an experimental value of the sun's mass. Next, you'll do a Google search and find a reputable source that gives you the accepted mass of the sun. You'll use the error calculation to find how far off you were. You'll do a % error calculation, and all of those calculations will be shown in your Notability file. That's our procedure. Let's see the next video, which walks us through the Excel work.